Welcome to day number 4. My name is Shani Danieli. I'm a postdoc at the IAS in Princeton. And we're very excited to kick off day number 4. Today we have quite a diverse set of topics to discuss, where the general focus is going to be putting the Milky Way in context and streams in the Milky Way, and thinking about its assembly, but also in context with other galaxies beyond the local group. You want to go one? Can you pass the slide? Okay, so we had 9 fascinating talks, ranging from results on the assembly history of the Milky Way and looking at some stellar substructure there in the inner and outer galaxy. And then the rest of the talk sort of slowly went further away to look at stellar streams and just the stellar halo substructure in M31 and in galaxies further away. It kind of naturally happened that the discussion of how and what can we learn by studying streams in other galaxies really already started yesterday. I think it already demonstrated what an excellent opportunity we're going to have today to connect the very experienced community that studies streams in the Milky Way with people that already started looking at this kind of structures outside the Milky Way. So I think it's going to be very exciting. Next slide, please. So since we didn't have so many talks, Chiske and I decided to try and give a quick summary in just one sentence for each one of them. So we'll have an easier discussion today. So the first topic that we have is substructure in the Milky Way and assembly history. We have heard from Rohan Naidu about the H3 survey of halo stars and how they found that the stellar halo is largely built from the big 3, so just a handful of accreted dwarfs. And the stellar streams likely came from globular clusters that fell in with these dwarfs. And then we've heard from Danny on their study of the inner galaxy using apogee data and chemistry from apogee and kinematics from Gaia DR2, looking in the inner part of the galaxy. And they had identified the stellar structure, metal poor stellar structure in the inner galaxy, Heracles, which is likely a tidal debris of Kraken, and that resembles also very similar chemical composition of low mass satellites. So this will be certainly one of the topics that we're going to focus on today. So then next slide. Then 3 talks by Sarah, Jeff, and Chiske focused on detecting and characterizing stellar streams beyond the Milky Way. So from Sarah, we have heard about the very cool half stream spotter that she's now applying to pandas data in M31, and results look very promising. I lost the slides. Do people still see the slides? Because I don't. Okay, now I do.
Working on it.
Okay, awesome. And again, there already has been very fascinating discussion on Slack about Sarah's results and what can we do better to confirm some of the streams that they are going to find. So I also suspect a lot of discussion on that. From Jeff, we've also heard about the MatCache survey with the Hyper Supreme Chem on Subaru, looking at stellar streams around LMC like galaxies, and also some work they are going to do with the Delve survey using the dark energy camera on Blanco, and the very cool tidal stream around DDO 44. And Chiske also told us about how with current data, we are going to be able to look to detect tidal debris around LMC-like galaxies, despite the low surface brightness already existing data, and especially in the Vera Rubin era. Okay, so next slide. Then we had a couple of talks that sort of talk about the interplay of stellar streams and gas, but sort of show quite different results. So Bene was inspired by NGC 891 that shows some stellar streams in resolved light, in resolved stars using the Hubble Space Telescope, and a possible association with some H1 detection. And from Adam, we have heard about the M81 group, showing M81 and its two pretty massive satellites, and this very interesting bridge of stars, this substructure that they detected by resolving the stars with the hypersupreme cam. Okay, so next slide for the summary. And then lastly, we had a couple of talks sort of focusing on dynamics of galaxies beyond the Milky Way. So we have heard from Johanna Hartke on how we can use planetary nebula to say something about the assembly history of dark matter halos, of galaxies beyond the local group. And it's very cool. She looked at a galaxy in the Leo 1 group, 10 megaparsec. That's pretty far away, impossible to actually resolve stars from the ground. But she utilized planetary nebula out to 23 effective radii, very impressive, to learn that there is a rising velocity dispersion at large radii. So maybe we can learn something about the accretion history of this galaxy and other galaxies. And then lastly, we've heard from Mireia Montes about an idea for how you can form galaxies that maybe lose their dark matter by possible interaction with a massive galaxy in the same group, showing that this galaxy shown here, NGC 1052 DF4, might have some tidal features due to such an interaction. So maybe we can, by looking at tidal stripping at the outskirts of dwarf galaxies, we can learn something about the dynamics of galaxy groups. So a lot of very interesting talks, very looking forward to discussing, and I'll hand it to Chiska to show us some questions.
Yes, thank you. So some of the questions that we thought we could focus on in the discussion for today, and we've divided this up in focusing on the Milky Way accretion history and focusing on going beyond the Milky Way. So if we focus on the Milky Way accretion history, some questions that came to mind are how well do we know the Milky Way's accretion history by now? What are the main questions that we want to answer going forward? And what observations and what theoretical models do we require to go further than we've gone so far, to go beyond what we know now? And in like smaller detail, dividing this up into smaller bits, there's, for example, a question whether should we focus on getting as much information as possible on the most major mergers in the Milky Way's history, or do we also want to focus on finding the smaller contributors? And maybe those are very interesting as well. Can we constrain accreted dwarf galaxies using the streams of their globular clusters, which connects to Rowan's talk? What more can be found in the inner halo, which connects to Danny's talk? Can we put constraints on connecting the evolution of the Milky Way's disk, bar, bulge, and other properties to the accretion histories that we find using stellar streams and information in the stellar halo? And what do we require from additional observations, and what do we require from theory? So, and then in the next topic, stellar streams beyond the Milky Way, the field is a little bit more open, we feel. And so the basic main questions are, what do we want to learn from stellar streams in external galaxies? And how can we optimally export local stream knowledge to extragalactic applications? What knowledge and what tools do we have now that would be very cool to use for extragalactic streams? And what new tools would we need? What new methods do we need to develop? And if in more detail, we could focus on questions like, what's the observational sweet spot to observe these? And how should we target that for upcoming instruments and surveys? And are there specific targeted additional surveys or follow-up that we would want or need? What additional theory of modeling needs are there to extract the information that is available in extragalactic stellar streams? Do we want to measure the halo masses and shapes? Do we want to constrain accretion histories? What do we need to move from an inside view in the stellar halo to an outside view on the stellar halo? Can we place stronger constraints on dark matter models with larger galaxy samples? And are there more synergies with other tracers, like, for example, the H1 or planetary nebulae or others? And are there possible additional connections to other extragalactic communities, for example, through other constraints on dark matter models? So those are the questions that we'd like to, or that we suggest to start this discussion with, or we'd like to leave with you for the next discussion. And then I think we can open the floor up.
Awesome. Okay, I hope everyone had nice discussions. So we'll try to do the same thing where people would like to share their insights or discussion with us. So just raise your hand and we'll take you one by one. So, okay, anyone from group number 1? Come on, I see a lot of discussion here in the running notes.
So I was in one. Dennis was there too. He took notes. So let me try to summarize a little bit. So we started talking about external systems and well, the difficulties of yeah, we don't have the same amount of data, obviously. We don't get good distances probably, and we don't get velocities unless maybe for some, say, globular cluster in an external stream. So we are a bit more hopeful about looking at, say, the power spectrum of gaps in those external systems. Also because we would, if we can go far enough out, we could kind of pick the host galaxies we want to target and then maybe choose ones which have less baryonic effects. You don't have a bar, you don't have a disk. Maybe that helps. But yeah, I think general agreement was that we this is very early in that game, and it's worthwhile thinking about it, and probably worthwhile doing this in the future. But nobody really knows exactly what's gonna be needed and what we'll be able to tweak out of the data. And then we also talked about how to maybe connect the Milky Way and its streams back to cosmology. Again, the problem that this is just a one specific galaxy, so it really would be nice to put it in a larger context, in a statistical sample. What else? Anybody else in the group remember what we talked about? We had quite a nice discussion, I think. But,
I think we had a nice discussion because I mean, Mark Fordall was in the room, so he's fed streams around M31. We're talking about how we have kind of a stepping stone to get out there. I mean, combined with like Sarah Pearson's work looking for globular cluster streams, we do have some nearby galaxies to try to make the connection to like doing dynamics and also doing stream gaps with like a nice nearby galaxy where we can get radial velocity information and perhaps even distances for some of the M31 streams. So yeah, it's a nice stepping stone. I think one thing we brought up was like falsifiable predictions. Like, can we make any predictions that we can really test with external streams? We thought perhaps the stream gaps was one kind of falsifiable prediction, where if we see no gaps at all, that could be kind of weird. But obviously we have to model all of that.
Yeah, I'll just add to the gap statistics point, which also brought up on Slack, is that I think we're just starting to think about gaps beyond the Milky Way, and something that will really inform what kind of observations we actually need to do is to try and simulate how well can we detect these gaps and with what kind of data, because I mean, it's gonna be hard. It's even hard in the Milky Way. Can we do anything with integrated light imaging or so I think it's really interesting to actually make this kind of simulations, injecting both into, say, catalogs and images, and try to see what kind of detections can be done.
Yep.
Okay, we have Eugene raising his hand.
Yeah, also about the gaps, I think we did touch on that, and the feeling was that maybe it's going too far. We could probably start learning something from kind of gross features and go for details like gaps somewhat later.
Okay, yeah, thanks. Yeah, Rohan?
I was just going to summarize my group, but it seems Sarah had like a quick point about gaps.
Right. So let's do Sarah first and then go back to you.
Yeah, just a quick note on that, that I agree. And it's been some really interesting conversation in the Slack channel on, for example, gaps in these thin streams and external galaxies. And I just want to say I very much agree that we now have shown that Roman can find the streams. And I wanted to definitely bring that up for discussion, that we actually still haven't shown that you could find the gaps and believe the gaps in the streams. And I just want to thank all the observers for chiming in, also thinking about what part of the isochrones are you actually probing, and will you just be able to, I think Adrian brought this up, would you actually know that the gaps are real gaps versus just fluctuations, because you're limited sampling of the data. So I agree, a lot more work has to be done, but I think it's very exciting prospects.
Yeah, that's awesome. Yeah. Anyone else on this topic before we move to the next group? Okay, I don't think so. So Rohan, go ahead.
Oh, one comment. I can't raise my hand fast enough. Yeah, I guess one comment I wanted to make was we just talked about some of the technicalities about interpreting gaps in external streams. And we kind of commented that perhaps, because it may be hard to measure the potential for kind of a separate discussion, maybe the stream gaps is a way to kind of get something without needing to know the potential. Then we said that you may also need to, probably need to marginalize over your unknown orbits of your globular clusters in order to really interpret what you're seeing. So you may still need to incorporate a marginalized potential. It was just some technical discussions about how to use a power spectrum analysis. But no, I think it's all really cool stuff. Yeah.
Wonderful. Rohan?
Yeah, our group basically talked about two topics mostly. So about the extragalactic stream detection and all the issues related to it, and how the accretion history of the Milky Way fits into all this. So I'll just leave you with some interesting open questions I think that we brought up, which would be great for all of us to collectively ruminate on. So thinking about extragalactic streams, it was brought up that before we go all the way out of our galaxy, what about the LMC itself, right? Like the LMC is in our halo. Do we observe or do we have hope of observing thin globular cluster stellar streams around the LMC and the SMC system? Will that require us to understand the tidal forces of the system in more detail than we currently know? Which I thought was a very interesting point. Another point was, as we go forth looking for streams beyond our galaxy, can we figure out some kind of a relationship between the mass of the stellar halos of these external galaxies, or even the mass of these galaxies, and what kind of streams would we expect around them, and then propagate that into our understanding of various models and stuff, and also feed in what we are learning from the Milky Way about the relationship between the kind of streams we are seeing in our own halo and the kind of accretion events we've had, and how much mass has been deposited in our halo. It was brought up that it's not just the total mass, but also the geometry of these various accretion events that might end up mattering for whether we detect these thin globular cluster streams in these external halos. Another interesting point was part of the motivation for us forging beyond our galaxy is because we want more of these clean GD1 systems, which are perhaps not as susceptible to perturbations from things like the bar and so on. So how many more GD1s do we expect within the Milky Way itself? Have we exhausted our senses of those GD1s? Will Gaia data release N maybe produce some more of them? What is that forecast looking like? As for the accretion history itself, one interesting point that was brought up was that when we're thinking about streams with regards to accretion history of the halo overall, in terms of the dwarf galaxies that came in, there's many interesting uncertainties about galactic, about globular cluster formation itself that are kind of up in the air, and nailing some of them down would be very helpful in terms of understanding what's actually the relationship between these accretion events and the globular clusters that we're seeing related to them. One interesting test that Rodrigo proposed was, do we know of like completely unperturbed, ultra thin like disk galaxies? And then what do we know about the globular cluster systems in those, you know, like merger-free, unperturbed systems? Like what can we learn then about what the base state is before you add in all this accretion stuff? And then finally, we kind of like, on a 5-year timeline horizon, we tried to imagine what it would look like to like build up like realistic models of the Milky Way, where you accreted something like SAG or the Gaia sausage Enceladus along with its globular cluster system, and then got streams out of it. And that was fun to imagine about, and just list what it would take. And it seems we might be able to get there on a 5-year time horizon.
That's great. You had quite a lot of discussion in half an hour. Okay, I think we have 2 questions follow up to what Ron just summarized. So maybe let's just start with Bene, who's raising his hand.
Yeah. I had a question. Is there any expected difference between centrals and satellites in groups, for example? So if you have a satellite that you end up with a larger halo or a smaller halo, more compact streams or wider streams, is anybody thinking how big the stellar halo should be in different environments? Is there a theory paper on that? It's a question I'm generally wondering about, and seeing this discussion, I'm like, oh great, so we're thinking about stellar masses, we're thinking about formation history. It's like, okay, so environment is what the galactic environmentalist of me thinks immediately. Does anybody can point me in the right direction?
So you're asking, how do we expect the stellar halos to look like in terms of their substructure when they are central galaxies versus satellites in a group environment? Is that the question?
Yeah, so most galaxies live in a group environment. Do they have more streams or less streams if they're the central versus the satellite? Do they have, this is a bigger halo or a smaller halo if they're centrals versus satellites, right? What do people expect? Is there an expectation?
Yeah, I'll echo what Robin said in the chat. Ooh, that is a hard question, which I totally agree.
Yeah, it's a good question though. I think it's a hard one from the simulation point of view, just because changing environments from one isolated Milky Way-like galaxy, even adding M31, is as far as we've gotten.
Okay, I'm sorry.
It's hard, but it doesn't mean we shouldn't try to do it. I think the little bit that I can say that we've looked at is that in paired galaxies, it seems like the pair does have some influence on like making sure that at least one galaxy has the brightest stream, but that is a statement with n equals 3 pairs. So take it for what it's worth there. We generally, I think the place that I would go for you to try to pay it forward is to look at people who have studied the evolution of satellites in different environments, and that's definitely the presence of the Andromeda Galaxy does change like the star formation histories of the satellites by a little bit, and from there I think you could extrapolate what might happen to the streams, for example. The larger the system, the earlier it forms and so forth, just from a hierarchical point of view. Actually simulating that with enough statistics to make any difference is probably beyond us at the moment. But I think you could start by just looking at what happens to the bound structures, and that's a little easier to know. This is related, I guess, can I just summarize what we said in our group because it's related to this? We talked about 2 things. One was about, that haven't come up yet. One was about the need for better statistics for predictions for streams around external galaxies. And I think this is related to the environment question because that's part of the span that you'd want to probe. And I think the way forward there is probably going to be that now that we can sort of simulate streams with full cosmohydro and a small set of halos, to try and use those to understand what baryonic effects we need to put in to a larger suite of dark matter only simulations in order to get the populations as right as we can make them. So that's really the next step. And then you could, with much less computational cost, try to extrapolate to systems in different environments. So I think that's the way that we were going to make progress. And then the other thing we talked about was that we took the chance to pick Roelof's brain about his lessons from Ghost on observing these things. And a couple of the things that came up, I tried to summarize. One was that the field of view matters, so we should really look to Roman to make a difference. And the other is that there are a lot of differences between observing stars in integrated light in a stream and observing stars in resolved star context. And all the questions that people were raising about what exactly we're detecting will have different answers for those two different things. And furthermore, we'll get from follow-up spectroscopy different information, whether we're putting a slit on a stream or trying to measure the spectra of individual stars. And the answers there depend on distance. What is the best way to go forward? So it's worth keeping in mind that once we get outside the Milky Way, there are multiple ways of observing these systems, and we need to understand what the selection function is for all of them, not just one or the other, because there are a lot of different answers. I'll stop.
Thank you very much, Robin. Yeah, that's super frustrating, but also challenging in a good way to try and understand.
Hey, we'll all still have a job.
Yeah, that's hopefully. Okay, so let's, I see that Johanna is raising your hand. I don't know if it's connected to any of the things that, the topics that were already brought up. If not, we'll do Emma for a summary and then you.
Yeah, actually, I was connected to Ben's question. I just very briefly wanted to chime in that while you can, of course, not look at streams and cosmological hydrodynamic simulations, what people have looked at as function of environment is the accreted fraction and how different kind of mergers, so major mergers, mini mergers, and even now micro mergers, these terminologies vary, but how these kind of different classes of mergers vary with environment. So for the illustrious simulation, there's, for example, Rodriguez-Gomez 2016, which might be something to look at. So while this is not directly related to streams, maybe this is something which may help to get a better understanding about how it varies with environment. And now we can go to Emma.
Yeah, I'll just mention briefly in regard to that from the observation side is that, you know, it's sort of only in the last 5 years or so that we've been doing surveys of groups outside the local group and, you know, finding all of the streams and modeling all of that. So that's also part of the story, like the Saga survey that people mentioned here in the chat. Okay, let's go to Emma now.
Okay, yeah, thank you. So I was in group 8, so I'll try and give like a little summary of the main things we spoke about. So we kind of focused on the external galaxies and what we can learn about external galaxies and then what we can take that back to learn about the Milky Way. So we talked about like if we're restricted to just photometry because it's going to be difficult to get any kind of velocities or metallicities, then it's still going to be important to kind of get the statistics of what kind of streams we have around these different galaxies. The number of streams can tell us something about the galaxy, you know, the shape, maybe it can kind of conserve something about the potential of that galaxy. Especially if we have lots of streams, we can kind of figure something out from the shape of those streams. But then one of the things that we spoke about that I don't think anyone's mentioned yet is the shells. So in our galaxy, it's quite hard to kind of find these shells and we don't know what their origin is, but maybe they're caused by these mergers. So we kind of linked that to the fact that, so if we want to find these mergers like Hercules or the Kraken, which are meant to be in the inner galaxy, looking at the streams of external galaxies and looking at the halo, we're not going to see them. But if these galaxies are what are thought to cause these like ripples and these shells, then maybe we can infer about these more like early on massive mergers that have sunk to the center from these shells. And maybe we can study these shells even better in these external galaxies because we have like a nicer view of them. But I guess it depends how limited we are if we need more than just the photometry and you know, when we want to get kinematics to kind of model those shells, we might be limited. So I guess our takeaway was that we see what the data brings, and then hopefully we can find out some nice things about the other galaxies and also obviously about the Milky Way from how it relates. But I think that was the main things, but if I've missed anything, anyone can chime in, so thanks.
Thank you very much, Emma. Yeah, that's fascinating. And I don't know if any group discussed that, but one other thing, other than not having 3D velocities and chemistry, is that we also sort of see the projection of the stream compared to the Milky Way. So, you know, even estimating the actual surface brightness, so the stream at different projections is going to give us very different, say, surface brightness, right, integrated. So, for example, Erin Cador-Fong, who's a student at Princeton now, with Jenny Green, works on that in the looking at low surface brightness galaxies at different projection angles, and she finds that there is quite a lot of difference, you know, when she injects them and at different angles. So that's another complication that will be also possible to look to actually learn something from, you know, simulating, injecting these streams. Okay, we're short in time, so let's go to Ivana.
Yeah, so I just wanted to summarize what our group discussed since it's related to this, focusing on what we will be able to get in terms of observational constraints of tidal features around external galaxies. So really, we think that what you'll be getting will be based almost entirely on photometry alone. The prospects for spectroscopy will not be good or probably even useful until we have things like 30-meter class telescopes, which for now, obviously, you shouldn't count on, but there's still a lot that you can do with photometry that has been shown from things like the GHOST collaboration, which have looked at things like the total accreted halo mass and color gradients within galaxies that's useful for formation history studies. And we'll also get something amazing, like, you know, imagine having pandas-like images, but for 100 galaxies or something like that, where you can get a full census of the stellar substructure in these halos. And you can do things like infer the number of significant merger events that these galaxies may have had. So one thing that we discussed, which I don't know has been emphasized yet, is that what is important is really providing a statistical sample of galaxies that we can use to interpret the Milky Way and place it in context, and also just to inform our understanding of how these galaxies form in general. So with the observed photometry, we expect that, you know, you won't have necessarily line of sight velocities on the sky, but you can run simulations to try to reproduce the observed morphology of these features on the sky, to learn about the dark matter distribution of these galaxies. So that's where we expect there to be a lot of interesting things happening. We also discussed various mass ranges. So, you know, we've focused mostly on Milky Way and M31 mass galaxies, but there are also dwarf galaxies where we expect it to be rarer, but who knows if you may find tidal features around some of these systems, and that would be really interesting. I think that is pretty much anything I discussed, but someone from my group should chime in if I'm missing anything. Oh, I wanted to mention just the importance again of these automatic tidal feature finding algorithms. And that's related to the work that, for example, Erin Cador-Fong has done using the Subaru strategic program data.
Yeah, that's great. We have still quite a lot of people that are raising their hands, so we'll try to get everyone. I'll just go by the order unless anyone wants to comment on something specific that we discussed. So Stella?
Hi, yes, I wanted to summarize the discussion in room 2 because we had also some discussion about the shells. So yeah, first we started talking about what we can learn about dark matter dynamics from streams in projection around external galaxies. And we did bring up that shells might actually be better and more informative about the potential when it comes to external galaxies, specifically because they could be easier to detect in the first place. And if you only have projections, it might be better because for shells, it's not so important to know the velocities because you assume all of the stars to be near their epicenter anyway. So perhaps you can still do something about the, constrain something about the potential of the galaxy. Then we went to discuss more about the Milky Way, in particular globular clusters within dwarf galaxies that are then accreted into Milky Way, and how do these clusters then look like? Someone brought up the 300 kilometers per second stream, which looks to be embedded in the Sagittarius stream, but has diverging radial velocity. So we were wondering if there's any work that has been done about that, and wondering perhaps Pao has seen that in his data of the Sagittarius. And then we moved on to talk about the globular clusters that are associated with the other merger events like the Gaia and Enceladus sausage clusters. And in particular, we were wondering if the Enceladus has been so disrupted now, how come the clusters that are associated with it, the globular clusters that are associated with it, are still not disrupted? They're not streams. And we were wondering if perhaps someone knows about how come they have survived so long.
Yeah, these are excellent questions. I don't know if anyone wants to comment on that. Or offline over Slack, that's also fine. No pressure here. Okay, I think if no one wants to comment, let's move to Chitske.
I think Raphael has been here for quite a while.
Oh, I'm sorry. So let's do Raphael first, and then we'll hear you.
Thanks a lot. I'll just say very few words to summarize some things of group 3, which haven't been well said to that extent before. The one question we discussed was, what would the Milky Way look like from the outskirts, put, for example, at different distances, to see what kind of streams, which we know a lot about inside the Milky Way, could we actually detect in external galaxies? Like, would Sagittarius be still visible in external galaxies, GD1, and what's the surface brightness cutoff or the progenitor cutoff? We also discussed what kind of tools we can use to model external galaxies, because we will never have the community effort to investigate what's exactly the potential of that galaxy, which we have for the Milky Way, with tens of groups trying to infer escape velocity curves and potential. So we thought that focusing on statistical properties could be one way forward there in the external galaxies, but also the need for fast n-body tools or semi-analytical tools to model individual external galaxies without having to repeat all the machinery we have for the Milky Way, but also trying to avoid the pitfalls we already know from Milky Way modeling, like mass anisotropy degeneracy, which in external galaxies where we don't have proper motions and not even hope for proper motions might be even more important. The question of what would the Milky Way look like on the outskirts is also interesting, because there have been attempts to identify subgroups, not dynamically, but purely chemically, like the Heracles subgroup. So could we just in color, just in spectra, find also dynamical subgroups or accretion history revealing subgroups in external galaxies? One last thing regarded distances that was mentioned earlier, but Zili had a nice example for and disentangling the group memberships of DF4, whether it was tidally influenced or not. It required 40 orbits of Hubble time to get the distance correctly from the tip of the red giant branch. So just a lot of exposure times seems to be important for getting accurate distances, and then just to properly understand the tidal environment, which galaxy is next to which one.
Yeah, thanks so much. Okay, I think we are almost running out of time, but we have Chitke to talk, and then we'll move to our coffee break.
Yeah, I just wanted to add some additional thoughts that came up in my room and that haven't been discussed in a broad sense, and that I wanted to provide to you before you go out to coffee break. So one is that there's been a few mentioned of wanting to see tidal debris around an external galaxy that's like very smooth disk with no bar, no spiral features, nothing. And that if you see gaps in that, then you can be more sure perhaps that this is dark substructure. But there was the excellent point made in my room that we can also use tidal streams that we see around external galaxies, maybe to learn more about their the dynamics of their tidal structure and their bar, which would be very interesting because that's very hard to do otherwise. And another thing that we talked about a bit that hasn't come up yet is the connection to other probes. For example, H1, that with upcoming H1 surveys, there will be a lot of measurement on potentials of these galaxies in the nearby universe. And that it would be very cool to tie that to what we see in the stellar halo. And that with really using the multiple probes that are out there, that would be, well, maybe the best way to get as much information out as possible. And the last thing that I wanted to leave you with is the thought of looking more at the tidal debris around the SMC LMC. Would we expect any globular cluster streams or really around the SMC LMC? And would those be, could we observe those? Can we learn more about that interaction before going further out? Yeah, so I think those points haven't been made in so far yet. So I think they.
Yeah, no, that's great. And so I think that, yeah, by now, at least two groups raised the point of looking at streams around the LMC. And I would be interested to discuss in our next session of discussion on can we actually do it given that the interaction of the LMC with the Milky Way is so messy? Or should we look at LMC galaxies, LMC-like galaxies slightly outside, like Jeff is doing? Where should we concentrate our effort, given that we know that the LMC interacted with the Milky Way? Okay, I think we are actually, we actually ran out of time, but that was really fun. Looks like the discussion went really great. So I'll hand it to one of the SOC members to send us to coffee break.
Yes, based on the discussions we've had in the first session, we found two breakout rooms, and probably Chitske should introduce them as the as the brain of the of the naming at least. So yeah, go ahead, please.
Well, I think that was in collaboration. So. But the first breakout room is the Milky Way in context, stellar halos, and galactic assembly. And the other breakout room is the context, tidal debris around beyond the Milky Way. So yeah, feel free to go to the room of your choice. And I will be in the first room, Shani will be in the second room, and we'll see you there. What are the questions that you are interested in? Because you're obviously interested in galactic assembly and stellar halos, tidal debris, everything. So what are the questions you're interested in?
Yes, Rohan, come on.
Yeah, so I think I'm broadly interested in how we can take our growing picture of the larger merger history of the Milky Way halo, like of the Milky Way galaxy, right? Like, you know, at redshift 2, there was this merger, at redshift 0.5, there was this other one, at redshift 0, there's the LMC merging in, lots of other smaller mergers. How can we incorporate our information from that history into what we are doing with streams? Like, how do we like what are the synergies? Because it seems there is information on the table there, right? Like if you know that a stream was born out of a globular cluster that was once born in like Sagittarius, right? Like there is information there, but what is that information? Like what can we learn further from that association? Like how do we like go forward, like kind of like bridging this smaller scale like stream structures with these like, you know, things that make the stellar halo. So that is a very broad set of things that I'm very interested in and that I'm hoping we can pull together on.
Yeah, great start. Is anybody? Yeah, Diederik.
So I think that is a really good point, Ron. And I think where we're starting to arrive now, and this is, I think, something really worth thinking about, is that we can start thinking about where globular clusters were in the progenitor galaxies. So if you look at the configuration of substreams and substructure within parent galaxy streams, you can start to think about what the density profile was of the globular cluster population of that galaxy. Now, of course, they're dwarfs, so this is severely Poisson noise limited, but you know, with some degree of Bayesian statistics, I have no doubt that this nut can be cracked. And that, I think, is really an exciting step, because you know, we were looking a lot at the surviving dwarfs to, you know, test dark matter models and so on, but there is a selection bias in which dwarfs survive and which ones don't. And you know, sure, globular clusters might not, or debris of globular clusters might not be the best possible way to get at this question, but it's definitely an avenue that we've not explored fully yet. And that's why we should think about it.
Great, thanks. Cecilia.
I had a quick follow-up question on, well, I guess some of this. So if many of the globular clusters, the globular cluster streams that we're seeing, and these globular cluster progenitors were accreted with a dwarf, what does that say about the luminosity of those dwarfs? Because there's a correlation between the luminosity of the dwarf and how many globular clusters it has. So these dwarfs must have been luminous enough to even have globular clusters associated. So does that makes, has anyone looked into this? The feeling I get is like, those are a lot of very luminous dwarfs. Is that consistent with what we know of the luminosity function of our dwarfs, or I don't know?
Sorry, should I raise my hand before I say anything? Jessica, you're the boss.
I think you're gonna reply now.
Okay. Yes. So this is exactly what we looked at in the latest Kraken paper. So basically, you know, once you do this decomposition of subgroups of globular clusters into associate them to specific progenitors, you can use the properties of the globular clusters to say something about the mass of the progenitor when they accreted. And then you can ask the question, okay, now that we've used an independent constraint, namely age, metallicity, orbit, to infer what the mass of the progenitor was, can we now look at the number of globular clusters associated with this progenitor to see if it actually sits on that relation? Now, the slight challenge there is that that relation evolves a little bit with redshift, because the epoch of globular cluster formation slightly precedes the epoch of star formation in most galaxies. So there is some slight evolution there. But within the trend induced by that evolution, it turns out this is entirely consistent. So this is actually one of the main arguments that the Heracles debris that people have now started to present at places, that you can be so sure that that's actually Kraken. Is there not enough ex situ globular clusters in the inner Milky Way that it must be the same system? So yeah, you can actually use those scaling relations pretty well.
Anna, did you have a comment about this or a follow-up?
Yes.
Because I think Cecilia wanted to reply.
Oh, I had okay, maybe Cecilia can go ahead, but I did have a answer to her first question as well.
Because I wanted to clarify, like I should have at the beginning, the scope, because I'm not so worried about things as big as the Kraken, but things that may have come in with one globular cluster, which is something that I think Rohan mentioned in his talk.
Yeah.
But thank
Anna,
you, Diedrich.
Yeah, what is
Thank
the...
you. No, Anna, you can scoop up a reply to that question as well, given that we also discussed it during the earlier breakout.
Yeah, I mean, we can come back to that, but I think like part of like Cecilia's first question was kind of, does the population of stellar streams like as kind of disrupted globular clusters make sense in this census? And like yeah, we didn't do any like detailed analysis, but what we are sort of independently finding in a paper to be posted to the archive at some point after the job market madness, we are finding that the stream progenitors were lower mass than the globular clusters that we see today. And so those scaling relations that we use now with the surviving clusters would not necessarily apply to this like larger population of disrupted streams. So I don't think it's like, you know, it still maybe that there is some tension, but it's needs to be worked out in exactly sort of what our expectation would be. And put in a different way, I think these disrupted globular clusters then are kind of telling us how the mass function of clusters evolved with time, which anyway, I think would have really cool implications for, say, James Webb coming up. And I don't know, maybe like extragalactic observers here can chime in on how observable these kind of lower mass, like 10 to the 4 globular clusters would be at high redshifts. But I think it would be like another aspect of this, the Milky Way in context that we might aspire to.
Great, thanks. And did you want to come back to the other point?
Sorry, I think I forgot what the other point was.
Single globular clusters.
Yeah.
If a satellite only brought in one globular. Okay. I can say something briefly about that, but I already spoke too much per unit time. So just very briefly, if you can't identify substructure in kinematic space or any type of phase space if it only has one globular cluster, of course. But you can say, okay, if there is a globular cluster that has a cluster of fossil streams sitting around it, which maybe came from these other, maybe more numerous lower mass globular clusters, then that tells you that maybe those streams and that one globular cluster came from a specific progenitor satellite. And then you can maybe use the properties of that one globular cluster to ask, okay, if we now go to cosmological simulations, what types of mergers deposit one globular cluster with this age metallicity and orbit? And it turns out that that actually is surprisingly constraining. So I had not expected that at all, but it turns out that that is a relatively narrow slice of the galaxy population that does that.
Well, but it doesn't, how well you can constrain it, doesn't that depend on how correct you are in having the correct Milky Way assembly history in the first place?
So what you would do is you would look at all possible, you wouldn't try to model the specific Milky Way. You would look at all Milky Way mass galaxies and go like, okay, across this entire population, what are the characteristics of the progenitors that deposit clusters on these orbits with these properties, single clusters.
Okay.
And of course, there might be a bias because we're sitting in the Milky Way and the Milky Way is unique, but yeah.
Yeah, but then the question is, do you really sample all the possible options?
Yeah, bigger volumes is better.
Bigger volumes, higher resolutions, always the answer. Thomas.
Mine is a small change of topic. So if Ting Li's comment is talking about this subject, then she should probably go first.
Yes, so mine is related to global cluster, but so I want to point out one thing is from, I mean, we don't have a lot of stream malicities, but all of the progenitorless global cluster stream, I think all the malicities at minus 0.2.2 and below. I think that's also interesting. We should think about why it's like that, because if we look at SAG and look at LMC, then you will see the global cluster in those kind of systems has a wide range from -2 something to -1, right? So but the one that we are seeing in terms of all progenitorless streams, so that disrupted a while ago, they are all very metal poor. Like Power 5 like stream, like they has a progenitor, but also like M92 recently, it's also very metal poor. So this global cluster, those global cluster stream that has a progenitor, it's more variance, like has very metal poor and a slightly metal rich, like in terms of between -1 and -2. And that's also something interesting, and we should think about that. And we'll also see if there's any kind of more metal rich progenitor last stream. That's also interesting to find. But I think so far from the observation, I don't think we see anything like that.
Thank you. So I think we now can go to Thomas.
Yeah. So one thing that I've kind of wondered about is accretion history work is right now we see the major merger going on is actually kind of two mergers. It's an LMC and an SMC. And I'm not quite sure about the frequency of like binary infalls in cosmological simulations, but I've always been curious if, say, for example, the GES was actually two things, like an LMC SMC pair. Is there a possibility that we could actually tell that at this point? Or if so, what would we be looking for in order to explore that possibility?
Great question, Rowan.
Yeah, so speaking specifically of GSE, right, I think it's a very interesting question to ask. We would expect a satellite of GSE or like a companion like the SMC to roughly end up like in similar integrals of motion space, but then we would expect it to have a track in like various chemical spaces that correspond to a lower metallicity, maybe lower metallicity, different star formation history track. So I agree that in integrals of motion space, it would be difficult to like try to recover them like separately, but when you combine like chemical information, you would expect to be able to pull apart, right, an LMC from an SMC. So one possibility is that the Sequoia dwarf galaxy, or like a lot of some of these other like retrograde material that we've found very close to where we think GSE lies in integrals of motion space, but these structures display distinct chemistry. It might very well be that they fell in together in one of these like associated groups. But yeah, that's totally a possibility that we should never discount and like have in mind.
Thank you. Shervin.
Hi, yeah, sorry. Hi, Ron. I mean, I kind of want to like just jump a little bit again on this thing on actually what Thomas brought up with the two progenitors. I mean, I can understand it if I were to look like specifically at like GSC1, let's say individually, and then GSC2 individually in chemical space. I would say yes, they look really different because there's going to be a different break, for example, in the alpha, alpha over Fe. There's going to be a different break in the knee, but but I think maybe, I'm not sure if like, do you think if it's like, if we're getting like more data, would we be able to actually really disentangle like these two different breaks? Because I mean, it's right now, like when I look at the, when I look at the plots in alpha over Fe, I mean, I have a bit of a hard time to really like convince myself like whether like, the Sequoia track is that different from the GSC one. I mean, yeah, there is a bit of there is like a qualitative trend, but like to really be, like I don't see like, for example, like, oh, there's two different knees and I can see them like perfectly. And I don't know if this is just because we just don't have enough samples, or is it just, or is it just that, maybe alpha over Fe is just it's a lame plane actually. Maybe we should think about barium and we should think about our process and like, increase the space. You know, I'm just trying to like provocative here, but you know what I mean.
Rowan, do you have a new hand or an old hand up?
It's a brand new hand.
Okay.
It's a hand raised in honor of Sherwin. I completely agree with that, right? Like in the sense that when you plot some of these chemical evolution tracks, like the theoretical ones, so in Catherine Johnston's group, Dwayne Lee had some beautiful work in his thesis about this, where you have all these tracks for different masses that are like going down with time. But if you like cut them off like very early at like, like 10 or 12 gigayears ago, like all of them look very alpha enhanced and fairly metal poor. So you don't have too much of a handle there. But 2 points. I will say that some of the knee work that's been done for like GSE and stuff with very high resolution spectra is limited to like the local halo and like with not like crazy like large samples of stars, right? Like not in the for that kind of the knee work has not been done with like thousands of stars yet, right? But we know that we are on our way to that point, right? But in H3, for example, for GSE, for like a lot of this retrograde stuff, we have like about 3,000-ish stars with like very high resolution spectra. And when you plot their MDFs, you do see like differences. Like you do see, for example, in some regions of phase space, like very clean, gorgeous unimodal MDFs, which are beautifully explained by simple chemical evolution models. And in some spaces, you do see like very bumpy MDFs, which peak like at very suggestive locations corresponding to like what some of these other high resolution studies have found. So yeah, so on one hand, I agree that like at very high redshift, a lot of stuff like looks very similar in like many of these chemical planes. But I also wouldn't like completely give up hope because the data is like definitely going to get better. And we are already seeing hints in like some of these large sample kind of studies where just by binning MDFs, we are able to like see like more structure than like one event versus multiple events.
Thank you. Before going, I wanted to ask Ethan, you commented in the chat. Would you like to speak about that?
Sure, yeah, I was just replying to the point that Thomas brought up, but as far as the frequency of these type of like binary infall events in cosmological simulations, I mean, it's really hard to find systems that look like the LMC, SMC configuration specifically, but if we have something in mind for, the type of kind of mass splitting and, accretion redshift that could correspond to Gaia Enceladus plus smaller event, that's definitely feasible to look for and estimate, rates.
Thank you.
Can I think follow up on that?
To that. Sure. I wanted to add to that for the people who don't know, if you go to higher redshift, multiple mergers become more common. But Anna, are you, or
I guess
Sherwin or Diederik want to add?
I had a question about like these mass ratios and sort of like for follow-up for Ethan, kind of what kind of observables, like where would like these differences kind of come up in dynamical space, not in chemistry, and if you have a sense of that, or if not, kind of how do we get how do we find them like in simulations?
What do you mean by dynamical differences?
Like if it is possible to disentangle just from the phase space positions of the debris at the present, whether it was like in the absence of chemistry, can we just like from the phase space identify 1 versus 2 kind of galaxy?
Yeah, that's a good question. I mean, I guess was it Yoji's talk? There was the talk on the fire simulations kind of touched on this, right? Like recovering from the phase space, right? The original satellite groups. I don't know. I would imagine it's very orbit dependent, though, and accretion time dependent, because the longer you phase mix, the more difficult it gets dynamically to disentangle, right?
No, I would imagine there's also, I guess, some sensitivity on the, kind of how tightly bound they were, like in the original group. Do you have a sense of like, do we have simulation suites that that are just kind of someone needs to go and look, or do we need to run new simulations to answer that question?
I think the answer depends on what masses you're interested in. So to get halo, if we're talking about the infall of 10 to the 10 halos or lower mass, then the binaries that you'd commonly find around them are probably 10 to the 8 or even lower mass than that. So you do need very high resolution, so probably suites of zoom-in simulations, which we have, but the numbers are still in the hundreds, not the not the kind of cosmological volume numbers that you can get in larger sims.
Cool, thanks. Sorry for the
Sorry.
interruption.
Okay, so let's get back. I think Diederik was first.
So I think in the context of what we're discussing, it is, so there are two things here. One is, I think as we just commented on, it's very important to not double count single merger events by just discovering them multiple times. It's equally important to not take one merger event and erroneously split it, or conversely, take multiple merger events, like if a binary falls in, and call it one thing. So this, of course, is a little bit of for me, it's sometimes a little bit of voodoo. There is some subjectivity involved. And in our discussion, I have the feeling we're kind of considering the ideal situation where the progenitor was the product of a major merger. But if that mass ratio is quite different, then it's going to become very difficult to distinguish between the scenario where it was one thing or one really massive thing with a small thing. I think we'll really struggle to ever distinguish between these cases. So maybe, right? Maybe we're confident enough that we can do factor of 2 science, and then we would be able to distinguish a major merger progenitor from, or sorry, 2 similar progenitors from one big one. But I'm personally not really that confident. So I think this is a really delicate question. And I think this is one where we really need creative ideas. We need to maybe not rely on just numbers or masses or orbits, whatever. We need to use context one way or another. And I don't know the answer, but I have the feeling that the answer will be in the direction of context. And I liked Shervin's point in that regard, which was chemistry. Yeah, we can look at alpha at large. We can try and look at other abundances. We can even try and split alpha. Maybe there are subtle differences there, especially when you talk about globular clusters, of course. We know that there are differences. But this needs brainstorming. And to finish on a brief plug is the successor of eMosaics, which is called EMP mosaics, is run using a repo with cold ISM and so on. But importantly, in this context, it has we're tracking the abundances of 34 chemical elements and their isotopes. So we're hoping that actually is going to help us do chemistry a lot more carefully and hopefully be able to help answer these types of questions.
Okay, thank you. Shervin.
Yeah, sorry, really interesting point, Diederik. Yeah, I think yeah, coming back to the issue about that Rohan also brought up with like sort of volume. I think also like when you explore volume, you can if we're talking about massive things falling into the Milky Way, you're not necessarily just thinking about like a single metallicity kind of object, right? That there's probably like a spread of metallicities, and so even if you in one part of the sky you see some sort of a trend, but then in the other part of the sky for the same structure you see another trend. I mean, it's not necessarily means that you're actually seeing 2 different objects, but you're just maybe if you had like, for example, like a some sort of like extended little disky puny but still massive enough for the Milky Way galaxy that fell in, that's probably also like, for example, you were touching on sort of the outer disk, right, in your simulation set, Rohan. And I think that's also something that perhaps we should, if things like Kraken and like GSE, like if these were actually really massive, that's also another area of complication. And it goes back also to one of the papers that Helmer also put out, right, a couple like just a while ago. So yeah, it's not just a matter of like 1 or 2, but it's also just like this one can be even like pretty damn complicated to start with. So, and I'm wondering if that also feeds back into the globular cluster population of that one object, right?
Alex.
I guess I had wanted to ask about kinematics, but I'll say something about the chemistry, which is that the thing that you get to constrain is star formation efficiencies, which is going to be pretty hard once you start going to higher redshift. So all of the alpha over iron tracks are not actually tracing things like stellar mass. They're tracing how quickly you form stars. And if everything's forming stars really quickly at similar rates and just stops at different times, you're going to get very similar chemical tracks, right? So that's going to be really hard. There are like a little bit of ways around this, like having you can tell differences in stellar masses if you can start resolving scatters in abundances, just because of the rarity of different, you have to go to neutron capture elements or look at resolve different core collapse supernovae to get scatters of elements, but that's really, really hard in the halo. You can do that if you have streams where you can say all of these stars are the same and therefore I care about the scatter. But without a dynamical or spatial association, there's no hope of doing that sort of work. The question I had actually was about globular cluster, because there's been talk about sort of the globular cluster kinematics, and I'm wondering like how well we understand theoretically the distribution of globular cluster kinematics. Like, is that something where you can have like a generating function where you like, you know, for a given satellite of a given mass that comes in, I can generate a statistical population of globular clusters that it should come in with, like the distribution function of globular clusters it should come in with. Like, is that something that we actually know pretty well, or is that something that is sort of, we can put in a model for it, but we don't actually know how good that is?
That's a good question. Rowan, did you want to say something about that? Okay. Anyone else? There's been a bit of discussion in the chat also about if things falling earlier, then they're harder to separate out, both in momentum space and in chemical space. So yeah, that goes back to what Alex said. I would think Diederik could comment on the globular clusters, but I don't want to put you on the spot, and maybe someone else is.
If someone else wants to go first, it's fine. Otherwise, I'm all right with being put on the spot.
I think it's you.
Okay. Yeah, I mean, I think so we've not actually looked at this yet, and we're doing a project with Helmer in eMosaics, where Helmer is looking at the globular cluster populations of accreted satellites.
Of lots of globular clusters around other galaxies, or is it like you're okay sort of looking at the distributions we have in the Milky Way satellites or something like that?
I think the problem is that the orbital space becomes, or the just 6D phase space becomes hyper degenerate once you only have projected distance and line of sight velocity. So this to me seems Milky Way science, and then you need to acknowledge that none of your zoom-ins will actually have the same assembly history of the Milky Way. So you need to approach it statistically and ask if the Milky Way is sensible within the distribution functions that you get. But doing this for other galaxies, I think, will be really tough going forward. Chemistry, always.
Shervin.
Sorry, I always take some time because I need to unmute myself and I struggle to find the button. But surely, like Diederik, like you have like predictions like for, you know, given mass spin, you know, you have like predictions for like what is the distribution of globular clusters with respect, for example, to the light of a galaxy. And I was wondering, like, you know, does that distribution generally, like, is there like some sort of a profile that, you know, you can sort of empirically like say, you know, if this galaxy is this mass, this is the type of profile distribution function I expect for globular clusters in that mass spin, right? Or, you know, to at least like motivate, because I remember we did some experiments like, I don't know, 5-6 years ago, and, you know, we came up with some like a bit of a silly recipe, but, you know, I'm just wondering, like, now that you have like these simulations and you can actually have these predictions, is there like some sort of information that you can have, generally speaking, for a given mass spin of like
yes.
the distribution function of globulars?
That information must be there. We're a small team. So if people are excited about certain questions, then just let us know. And we're very happy to work with you. But no, I mean, yeah, I'm sure the information is there. The physical question I would have is to what extent indeed details like assembly history might actually bias you in one direction or another when you try to come up with sort of a generalized form. And then the question is, as a result, if you look at one galaxy, how applicable is your general form? That would be the only reservation. But yeah, this is a great idea.
Alex.
Yeah, so kind of coming back at this from more of an the observational perspective. Do we have a good handle on what the observational selection function is for Milky Way globular clusters? This kind of work has been done, you know, with the DS collaboration and Ethan Naller's work, and you know that was a very heroic feat. Do we have to do something like that for globulars? Or has it been done already?
Other Alex was first.
I'm totally unrelated. Yeah.
Oh, okay. Then let's ask Rohan if he's related. No? Anyone related? Anyone has an answer for Alex?
I mean, I've talked to Alex Wagner and Keith Bechtel a lot about this, and basically have become convinced that it's extremely hard and that I don't have the expertise to tackle it. And that it's probably, like you said, Alex, another 5 to 10 year time scale effort to really do this well. But it's crucial, I think.
Thanks. Okay, so other Alex.
So one of the completely unrelated question I had was about sort of observational things that we probably should be looking for that we can't see very easily. So can we use like observations of features in other galaxies to say, oh, actually this is a thing. Is there anything that like we have seen in other galaxies or we expect to see that is really hard to detect in the Milky Way, but we should be looking for, or we expect, like, is there anything in that category? Like shells is one of that is, yeah. So that was, that's the first thing that I thought of, but I don't know if there's anything else.
This connects actually a little bit to a question that I wanted to ask for all of you because we are in the last few minutes. And one of the things I was wondering out whether there's more connection to what we see in the tidal streams versus what we could be measuring from the disk and the bar and bulge formation, for example. And that's something that people have done more in external galaxies, trying to connect what you see in different components. But anyone of the three hands that are up wanted to reply to this specifically?
Yeah, so I was just been thinking about this, you know, the fact that LMC, the LMC we think is causing the Milky Way center of mass to move, or at least the disk to move, would imply that if you were seeing this in an external galaxy, you should see some lopsidedness. That is, you know, sort of a deviation of the center of, so the isophores. And lopsidedness has actually been observed in external galaxies for a very long time. And I think if nobody has actually looked at either in cosmological simulations or observations into whether or not, you know, this could be related to this kind of tidal interact, I mean, sort of infall. And I thought that would be interesting to look at.
Absolutely, thank you. And I see a few thumbs up and people nodding. Would anyone want to comment on that directly? Because otherwise, Tom had a hand up too, but he went down again. Did you want to mention?
Yeah, well, mine was related to Alex's comment about can we learn about substructure in other galaxies and work on this one. And I was just going to chime in and say, yeah, shells are probably here, but they're really hard to find from inside the same galaxy. So that's something that I think needs to be addressed and that I'm working on addressing.
Awesome. I completely agree.
Yeah, so we're gonna discuss the context or what can we learn from other galaxies, sort of both just, you know, on themselves, but also putting the Milky Way in their context. So anyone wants to raise anything? We discussed so many things briefly in the previous session, like shells and H1 and follow-up of streams. And we have a bunch of the speakers here if anyone wants to ask some questions. So we have, yeah, Sarah and Adam and Jeff. So yeah, who wants, let's see. Okay, anyone? Yes, Sarah.
Yeah, I just had one point that I'm not sure came up in the summary, but apologies if it did, which is that it'll also be really exciting now that we have with LSST and Euclid so many, like hopefully thousands of streams, dwarf streams around external galaxies, that we're finally in a place where we should be able to, based on, for example, David Hendel works and some of Catherine Johnston's older work, maybe do more statistics on infall histories and accretion histories and what type of things fell in and on what orbits. And I think we're not fully ready to deal with that data yet. I think it could be very cool for the community to come up with clearer questions of what can we compare it statistically to lambda CDM, and what would kind of be the distinguishing part where we think that something's off or it's consistent. I don't know if anyone has thoughts on that, but I'm not really sure we're there yet, at least. So that's something for the community I think we could work on in the coming years too.
Yeah, so does anyone know if the LSTC, okay, I see that Adam is raising his hand, so yeah.
Oh yeah, I just wanted to follow up on that point. I agree. I think, you know, discovering, you know, all of these streams and the upcoming wide field surveys is kind of the thing to discuss. And I just wanted to bring up the point that, you know, as someone who's tried to do a lot of this already with kind of existing instruments, wanted to talk about, you know, maybe bring up the point of developing some of the infrastructure that we're going to need to actually do this, right? Developing kind of community-based methods for star galaxy separation and community-based methods for, you know, stream finding and kind of marrying those two things together, because I think that's what it's going to take, because, you know, the extragalactic stellar halos are a lot different, you know, from the Milky Way. There's a lot more contamination and background sources to deal with, and things get very tricky.
Yeah, Jeff?
Yeah, no, I going back to Sarah's point, you know, and we've, geez, was that like 4 years ago? Robin and Adrian were part of this conversation where we were discussing what are we going to do with, you know, yeah, when Ruben finds, you know, hundreds of thousands, maybe millions of, you know, unresolved tidal features, low surface brightness features, you know, how do we find, first, how do we identify all of them? Second, or even candidates, I guess. And then second, how do we classify all of those so that we have the sort of statistical sample that Sarah was sort of alluding to, you know? And so one way that we've thought about that, and I can't say anything has really progressed since that time when we talked about it like 4 years ago, but the, you know, one way we thought about it is it's really easy if you can identify candidates, then you can use Zooniverse and have a citizen scientists classify things, and you can even do very simple things where you classify the morphologies, but you can also, even if you want to get really fancy, do super low res N bodies that they tailor to actually reproduce the features, so that you get some coarse sort of properties of the features. And so there's some, you know, this was a discussion we had a long time ago, but it's also something that that within the LSST Galaxies science collaboration, there are also people who are normally, you know, looking at distant galaxies who are thinking about this as well. So it is something that I think will take a lot of effort, but will be extremely fruitful.
Yeah, this is such a fun idea, the citizen effort. So I was actually wondering, I don't know if anyone checked it. So the HSC, since, you know, we've seen so much successful work from Adam and Jeff on using HSC on Subaru data, Did anyone look at, or is the data good enough to use the HSC SSP? So, the wide survey that covers, or is going to cover 1,400 square degrees, but already quite a lot of data is public, and they're going to have another public data release at the end of 2021, I think. So there is a lot of data there. It's the wide survey, so it's not as deep as other patches, but I don't know if Adam and Jeff has a knowledge of, is it deep enough for us? Because it covers a pretty wide area. So there must be some interesting galaxies that fall in the footprint, and or even isolated galaxies, right? Which are not extremely low mass that might have tidal streams around them. So I don't know if you've looked into that, but that's, I mean, that's going to be an amazing data set in 5 bands, which we can then follow up. I don't know if anyone looked at that.
Yeah, I think oh, go ahead, Jeff, I'm sorry.
Oh, no, I was just going to say, I looked in the first data release of the SSP, and there aren't really any interesting local volume galaxies where we could do resolved star searches, but, of course, you can do stuff like Aaron Cato-Fong's work and Johnny Greco's work and find all kinds of unresolved tidal features.
Yeah. Yeah, Adam, and then we'll do Robin, if that's okay.
Yeah, I was just going to say, I'm not exactly sure which sort of galaxies are covered in the wide survey, but my understanding is that the wide survey is actually more comparable to the sort of depth that Jeff and I have done with HSC, Mad Cache and our survey, and I think the sort of deeper pointings in the SSP are even deeper than that. So I think the wide, the wide portion of the strategic survey program could be interesting if there are interesting galaxies that have been looked at. There's actually a lot of archival data. Some of the Japanese groups have actually done some of the other nearby galaxies using what I would say is almost an absurd amount of Subaru time and getting really, really deep in several of these filters. So that's something that, we haven't really, I don't think either of our groups have really worked with much, but there's actually quite a bit of data that exists on some of these nearby galaxies with Subaru.
Yeah, I think that's pretty good news if you think that, that's deep enough, because I checked at some point and I saw that the HSC wide actually covers, for example, quite a lot of Saga groups. So, over there we have even more information, right? Because we know also a lot of stuff on the satellites, which is nice. Okay, sorry, Robin, please.
No worries. Really quick, I think, Jeff, if I'm remembering right, we were planning to use that whatever public data was coming out of that as a precursor to test out StreamZoo if we did it. Was that right?
Yeah, that was sort of the plan.
That was the plan.
And it kind of didn't go anywhere yet.
All kind of
but
stuff happened. We just
right.
need more person power, I think, on that project. So if anybody is interested, maybe we could revive it. Maybe we should start a thread in Slack on that. See, or talk about it tomorrow.
Yeah, and I also think I should bring it up with the the Galaxies science collaboration, just to if there are people who are doing similar things, we can coordinate everything in a community effort.
Yeah, the Galaxy Zoo people are all on board already, though. It's really easy to set up the interface. We just have to decide what questions we want to ask.
Yes, Sarah. Yes, this is going back a bit to what Jeff said earlier, but I just wanted, this came up in discussion yesterday too, but just wanted to point out, I can link it in the chat, a paper by David Hendel that actually already has done a lot of advancement in classifying external galaxy streams versus shells and thought about what information we can extract. So I just kind of wanted to point out that that type of thing already exists. And I think we're lacking a little bit theoretically on what we'll learn for all these very cool streams we'll find. And I think Dennis, as far as I know, you've also thought a bit about how we could maybe use particle spray type modeling to rapidly generate libraries of external stream galaxies, right? To maybe guess something about their potentials. I don't know if you want to say something about that.
Yeah. Can I go?
Yeah.
Yeah. So yeah, no, I think it's a really great point that we haven't done very much work on fitting external streams. I mean, some work has been done, like by Mark Fardal and Nick Lamorisco, who both fit external streams, but I think really probing the information content is something that's left to be done. There are, I mean, it's not 100% clear what we can learn with just projected information. So as someone said earlier, we're mostly going to have projected information for these streams. There is a degeneracy that exists if you don't know anything about the potential, just because you can always trade up the mass for the velocity and get exactly the same stream on the sky. But if the stream does pass close to a known baryonic component, this was when that came up in our breakout room, that, you know, for the Milky Way, we're adding in information, not just from streams, but from like rotation curve measurements when we fit streams, like including a disk, which is known ahead of time. You can do the same thing with an external galaxy. And so like you do know part of the potential, but you have an unknown dark matter halo. I think there is something to be gained there. And then there's also questions about, you know, just the morphology of streams. Like if you're in an aspherical potential, streams will precess in their orbital planes. Can we see that in external streams? There's also things about how the stream width varies due to kind of orientation in flattened potentials. So maybe we can learn something from the morphology. I think we definitely need to do more work to really understand what can be learned and, you know, how much it helps to add in spectra, for example. Like do we need just one spectrum to break the degeneracy? Can we get one globular cluster? Is that enough? So a lot of work needs to be done to understand what we can learn.
Yes, Sarah.
Yeah, related to that, I just kind of wanted to put Tomer on the spot and ask if you've thought about the cool work that you've done, if that could maybe be applied to external galaxies, relating to what Dennis just said about morphology.
Yeah, I think it's, I mean, I think Dennis hit it on the nose, right? It's like the ability to work only in morphology, because we're so limited in the other types of data we'll get, at least initially, is obviously huge. But I think we need to do a better job of understanding what that looks like. I think this was mentioned by maybe one of the groups in the first session, but I would be very interested in some sort of work around what does the Milky Way look like? What do the Milky Way streams look like at various distances? And what can we, you know, given what we do know about Milky Way streams, what would we be able to infer from seeing similar things far away?
So imagining the Milky Way was an external galaxy and going out of it.
Yeah, and
I mean,
you know, yeah,
that should be like a pretty straightforward exercise, right? Just to push the Milky Way with all of the stream content that Adrian has, all of this beautiful, you know.
And yet nobody's done it yet.
Yeah, and just like let's push it and like rotate it at different angles, right? To look at different projections. I think it's fascinating. Yeah, it's such a good end.
Where people have done that is in M31. There was a paper a while ago. I think it was a very like first stab. I think it was Nicolas Martin who did this to try to go from Cooper et al. To as if the Pandas survey had seen it. And the results were kind of weird, so I think it's worth another look.
We can talk about it in the next stream workshop next year to see the results by someone from here. So I wanted to ask Dennis whether we're going to work on modeling external streams. Are you going to use, like, what did you have in mind to use for as your data? Because there are quite a lot of streams that are already known by, say, the work by David Martinez Delgado, right, who has done, and of course, like Sarah is also part of this effort. So there are already so many streams known in integrated light, and most of them are sort of, you know, gigantic, sort of like sedge type of streams, if I understand correctly. So is this the kind of data that we're going to try and use? Is it constraining enough to learn something? Is it going to be combined with information from global clusters and kinematics of the global clusters, etc.?
Yeah, I think that's a really good question. So we actually have, it's almost a part of the effort that Sarah Pearson mentioned, like with David Martinez Delgado, for looking at external streams, and we have started fitting some of the streams. So right now, these fits were just based on fits on the sky, like positions on the sky. It was done in a kind of bit of a haphazard way, to be honest, in that we someone had looked by eye and kind of identified the stream location. So what we do there is we take our technology from the Milky Way and basically add in kind of additional hyperparameters to like account for the error in by eye fitting, right? But like one thing is we definitely need some automated way to extract stream tracks with uncertainties from photometric data. There are things like that for the Milky Way. People know how to extract these tracks, but it just hasn't been done as well, I think, for external streams, at least ones, you know, beyond M31. That's part of it. But then in terms of the way the fitting techniques work, it's like kind of like the Milky Way, where you add in information that you do know from closer in. So most of the galaxies that have streams also have like a disk or like some kind of rotating component or spectra of like globular clusters. So you can do Schwarzschild modeling to get a decent mass model. And so for the ones that I've fit, that this should be coming out in the literature hopefully relatively soon. But we basically just took photometric data and we're just trying to know, can we fit a stream to that? And the answer was yes, and it's pretty easy. And you know, one cool thing I think that maybe hasn't been put in the literature yet, but is kind of obvious consequence of everything people know, is that it actually helps us that we're mostly orbiting in like an NFW potential or something like that, because the kind of orbits you get are very different than in a Keplerian potential, where like a rotated ellipse is still an ellipse. But when you rotate kind of NFW Rosetta pattern, you get a kind of don't get another Rosetta pattern, you get something a little bit different. So like when we fit external streams, we're actually able to get the orientation of the stream really accurately. Like there wasn't like a degeneracy in kind of rotating the stream onto its side and just making it bigger. So there are things like that, you know, which I think can be done. But in terms of fitting the potential, what we found was there was basically no constraint. The only constraint we were getting, if we freed up the dark matter component, was that we had to have some amount of dark matter. Because if you just get rid of the dark matter, then the baryonic component dominates. And that has a different shape for the orbits in the outskirts. Because we have a stream, let's say 50 kiloparsecs out. As far as the baryons are concerned, they look like a monopole, kind of like a Kepler potential. And that would look like an ellipse. So adding in the dark matter gives you this different shape of the orbits, and that lets you fit the stream. If you fit it, probably you can't fit it just with the baryons there. So what we were getting was we needed some dark matter. But we could have an arbitrary amount of dark matter, because you can always scale up the dark matter and scale up the velocities and still get it to match. But this is all like, yeah, cutting edge stuff. And I will say there are some students working on this. I know I have one PhD student who's going to be starting to answer these questions, hopefully kind of figure out what's the information content as we add in radial velocities. You know, how many do we need to say anything? But it's going to use the tools from the Milky Way and just project them. So.
Okay,
yeah.
Sarah and then Mark.
Yeah, I was going to say that's really interesting. Also thinking about how unique are these solutions that we find. I think that's an interesting point that you're bringing up. And also, is there any information about the halos at all? And I think that'll be very important for the community to know. But I was actually going to ask Mark also, based on your experience doing this for external streams, if you had anything that you learned you want to share.
Well, I'd say for things like fitting the potential, there are some areas where just having very, very, very crude distance, or even this may be fantasy, proper motion measurements can be very useful just to break degeneracies. Like, for example, if you can get, spectroscopy is easier. So you say you get radial velocities along the stream, you can see a gradient or something like that. If you can figure out if one part of the stream is closer to you than the others, than another part of the stream, that can tell you which way the stream is going, which otherwise is totally ambiguous. So that can be a very useful thing. But in general, yeah, fitting the potential is going to be a lot harder in external galaxies, and you get less categories of phase, less dimensions of phase space the further out you go. So as we were talking in the earlier breakout session, the questions that you focus on may wind up being kind of different in external galaxies. Like we might be looking kind of at the stellar populations of the streams. Like what is the, like can we place constraints on the age and look, like maybe link those up with morphology, or maybe, maybe like big kinks and wiggles in the stream are something that you can detect even if you can't do tiny gaps. So it might be, counting, building up statistical samples of, you know, how often do streams like kink as if they're, you know, as if they've been hit by something. And another thing that we haven't talked about much of this at all is gas streams. I mean, I don't think anyone's talked about the Magellanic Stream. Adam's result on M81 were very, very impressive. You know, so those may be rare, but that's a case where you see now stellar streams and gas streams, and there's clearly a connection, but they're clearly also different. That gives you a totally different, like we don't even have that in the Milky Way, right? There's no Magellanic stellar stream to compare to the gas stream. So that may be able to tell you both things about the dynamics of that system and also about the hydrodynamics of the system, like, you know, effect of a hot halo, or, you know, the general gaseous environment in that system. And there may be other such examples out there that we haven't, you know, M81 is a known case where the gas, like the gas streams were already known, and it's pretty spectacular, but, you know, with more work, maybe there'll be other examples like that.
Yeah, thanks so much. Robin?
I had a quick question for something Dennis said, and it's not necessarily for him particularly, but if you can distinguish that the dark matter has to be distributed in a different way from the luminous matter, that already is a test of some models of alternative gravity. I wonder if you'd looked at that.
Oh yeah, Dennis, go ahead, sorry.
No worries. Yeah, I mean, what I had tested was just, you know, whether if you add in, so like if you take the dark matter halo, which has been derived from Schwarzschild modeling, and just let it be free, just scale it up and down, and also scale the radius, you know, can you find, do you need dark matter there or not? And the answer was you have to have some dark matter there. Now this goes back to what Sarah was saying in terms of finding multiple solutions. So within the dark matter halo, as long as there was enough dark matter there that it dominated the potential where the stream was, we had this continuous set of solutions where you could trade mass for velocity. But as the dark matter gets very little and the baryons dominate, then the kind of potential class is changing. And now you're dominated by this baryons, which is a very different set of orbits. So there could be a totally different solution just with the baryons, which I didn't test because my goal wasn't to probe the potential in this paper, just to kind of do a kind of starting idea for Madison, the PhD student, to get a sense of what we can hope to learn. But I think in principle we should be able to, just because of what I said about the orbits being a different shape in a Keplerian potential versus a NFW potential, I think we may be able to show that we do need either like an extended dark matter component around external galaxies, or that the force fall off is different than you expect from Keplerian. I think that probably that can be shown because of the way orbits look in general in Kepler versus other potentials.
Yeah, so I think this is an example of how you have to change your questions when you're looking at external galaxies. So I think symmetry arguments and tests of the symmetries of the potential, for example, are something that we should look into more. I'm talking mostly to myself, but also to other theorists, because of the kinds of effects that Dennis was saying, what kinds of orbits you're likely to get based on the symmetric, based on the approximate symmetries of the potential. In order to really pin that down beyond, is it Kepler or not, you probably need some kind of prior from cosmological simulations, but at large distances, you could get away with that from probably dark matter only. It's just a thought.
Cool. I want to connect a little bit to what Mark, oh, sorry, Sarah, go ahead. If I was about to open a new topic, but go ahead. If you wanted to comment.
Yeah, no, it's almost the same. I was just going to echo all of that, saying that I think it's really interesting and important for us before we get so much more data that we learn what the questions are that are relevant, and maybe switch our focus to, if we can't learn, I mean, we don't know that yet, but if we can't learn that much about potentials, maybe we switch our focus to more of the things that Mark was mentioning. But I think we don't know that yet. I think it's just going to be important to kind of have that in mind as the data start coming in, so we're not just all searching in blind and figuring out 5 years later that we can't actually learn about the dark matter shapes from external galaxies, for example. So I think all of this is very important.
Yeah, so I think now the point that I wanted to raise connects both to what you just said and what Mark just said, which is, so Mark mentioned that, if we're gonna have a little bit more information, for example, some stellar populations along the stream or some velocity gradients, we're gonna, this is sort of crucial information beyond the just projected morphology of streams. So this is sort of like a question for discussion to observers or anyone else that understands these kind of things, of what's going to be our sweet spot for this kind of follow-up. So, we can try and find all of these streams that are pretty far away, but if we cannot do a meaningful follow-up with, say, spectroscopy or even very high resolution imaging with Hubble or JW, maybe it's worthwhile to try and focus our efforts somewhere else. So let's try to combine our minds and think, where should we look and what instruments should we try to use? So for example, so I saw that Charlie very briefly wrote on Slack that maybe we can do integrated light spectroscopy with instruments like MUSE and KCWI. So I don't know, I mean, there are a lot of very excellent observers here. So if anyone wants to just like share thoughts, it doesn't have to be accurate, because I don't think we really thought about it deeply, but we can start to think about it together. Adam and then Ivana.
Yeah, so this is a really good question. I think kind of my rule of thumb that I've been thinking about over the past few years is kind of 10 megaparsecs. Anything within 10 megaparsecs, we can sort of combine useful ground-based stellar populations with things like HSC or Rubin, with then reasonable depth with Hubble, with W first as well, Roman. And so I think 10 megaparsecs is really that sweet spot. We can also do things like combining those space-based resolved stellar populations. You can do things like co-added spectra of different features if they're bright enough. So I think that really is kind of the distance regime where all the different, that's the sort of Venn diagram of all the different techniques that we have to be able to measure these different properties all kind of coincide in that kind of volume.
Yeah, I totally agree about the 10 megaparsec local volume regime to begin with. Ivana?
Yeah, so I just wanted to speak a little bit about the spectroscopy side of things, since I've done a lot of work with spectroscopy of resolved stars in M31, which is often used as an example of what we might be able to achieve in galaxies beyond the local group. But I think it's the timescales that matter. I'd like to emphasize that our prospects for doing anything with resolved stars in terms of line of sight velocity are not good beyond M31 and will not be for a long time until we have something like 30-meter class telescopes. Then we would be able to do M31-like studies, perhaps out to 2 or 3 megaparsecs. But again, the data quality will still be low and it will still be challenging. But we should be able to get enough information where you could do dynamical modeling of streams in this case. So for people who are interested in something more near term, I think that, as Charlie mentioned somewhere in the Slack, you really need to consider only IFU spectroscopy for now, which I'm not an expert on, so I don't know what kind of information you can get out of that, but just something to think about for the future.
Yeah, so I mean, I think that, that was a really good point, because we have, in the last, it's fairly new, right? All of these new, very sensitive IFUs like KCWI and MUSE. But I mean, people have recently started looking at low surface brightness galaxies. But the question is, whether there are equivalent stellar streams that have high enough surface brightness, still low surface brightness, but high enough to get stellar populations. Yeah, it's going to require a lot of exposure time. But yeah, just what Mark mentioned made me think that maybe we can just place the IFU on different parts of the stream. And what Adam just said made me think that maybe we can combine, for example, imaging with Hubble in the UV, which can help to break some degeneracies about age and metallicity. So I think that IFUs is a really good idea, though, hard, difficult to get time and like very long exposure times, but but I think that's sort of like the best idea to move forward. Ivan, I don't know if you're raising your hand to say something else or it's from before. No, okay. Anything else? Did Adrian do we have three minutes left? I don't know, I just saw 3 minutes, okay.
Yeah, I think something like that. We have just a couple of minutes left, so.
Sounds good. I had a question to, I don't know, people that, so someone brought up the ghosts survey, even in the previous discussion. So yeah, can someone sort of like summarize what did we learn about sort of substructure and streams from the ghost data? Because there is quite a lot of data, right? And pretty deep. So I'm sorry if it's a simple question, but it will be useful. Adam, yeah.
Yeah, I'd be happy to kind of summarize. So one thing about ghosts was that it was definitely not designed for characterizing large-scale structure, like substructure, with that in mind. It's sort of pencil beam kind of survey design right along the major and the minor axes of like a dozen nearby galaxies. And they also targeted kind of this 10 megaparsec distance limit, right? I think there might be a couple that are at 12 or so, but it was largely within 10. There are some, there were kind of some isolated cases within GHOST that did kind of either intentionally target known substructures around nearby galaxies or just kind of serendipitously fell on something. But I think the main bit of learning that we got from GHOSTs was just the ability to characterize the accreted component of the stellar halo, right? And the the realization that most of the stellar halos of Milky Way-like galaxies, at least along the minor axis, are dominated by accreted stars and not necessarily in situ, right? So that's kind of that was kind of the main result, and this was something that Richard D'Souza worked a lot on, Richard and Eric Bell, and kind of verified with the illustrious simulations as well. But I do know that so Eric has a former undergrad now at SpaceX, so this is kind of his side project now, but still continuing some work, Matt Cosby, that he did on M83, and one of the ghost fields around M83, I'm sure that some of you remember this beautiful stream that was detected in integrated light around M83 years ago, I think back in the 90s, David Madlin. And the ghosts, the ghost data on that stream looks really beautiful. So they were able to do some kind of quantitative, some really quantitative work there, combining the integrated light data with the stellar populations just from this single HST field, and we're able to get the sort of metallicity and mass of that galaxy, which turns out to be, the progenitor turns out to be probably something like Fornax for that stream. So if that gives you a sense of in integrated light, we're able to see these structures that were these streams that were formed from galaxies 10 to the 7, well below Sagittarius, right? These are easy for us to see, but we can learn a lot from just from the stellar populations alone. I don't think there's any kinematic data that exists for that structure specifically. But yeah, I don't think there's any other interesting substructure streams that I know of in ghosts, but that was a cool one.
Thanks. No, I think it's really useful to know, because one sort of pipeline that we can think of is, after detecting these external galaxies, external streams, is then to place the Hubble pointing on sort of like different areas of the stream, to hope to try and constrain different stellar populations, and see how that goes. Like, it's good to know that the Hubble data was useful. Okay. I think that Adrian is closing the rooms. So yeah, thanks so much for the discussion, and please feel free to share all of that with the larger group.
So would anyone want to share some of the discussion of the breakout rooms into the main room? What were the most interesting points that you think were discussed? What should we think about more as a whole group? Sarah.
Yeah, I could just start us off of what we discussed. So one of the things I found very interesting is just maybe rethinking what type of questions we need to ask to learn from external galaxy streams. So we have a few examples of streams that have been modeled, but we were kind of discussing what it would take to actually learn anything about the dark matter halos and shapes of external galaxies, and that maybe that's not the question we can actually ask for external streams. Maybe it's more useful to think of it, again, statistically in terms of morphologies and infall times and what type of accretion histories external galaxies have. So we just discussed, with a wealth of upcoming data that's going to be available, what will be the questions to ask as a community. And I think we don't really know yet. So we agreed that it's important the next couple of years that we really work together also with observers to ask what are really the defining observations besides just morphology of a stream. And we were discussing a bit like alternative ways of getting some kind of velocity gradients and measurements along the streams. But this was my biased take, so other people should chime in.
Thank you. It actually matches a bit with what we discussed in room 1 on the assembly history, in that we could actually learn from external galaxies and learning more about what other traces we could use to learn about our own galaxy's assembly. Anyone else, or anyone wants to comment on that?
Can I say one quick thing?
Yes.
One thing that came up in our session, because several of us were there, was that a while ago, Jeff Carlin and I and a couple other people were spinning an idea for stream zoo, like getting people to identify streams with the Galaxy Zoo interface. And the HSC pilot, like SSP, is essentially a good test data set for that. So I think Jeff and I were like, we should probably fire this up again at some point, since we never got anywhere with it. So I think I'm going to make Jeff start a thread in Slack. And if you're interested, the reason this didn't get off the ground before is that we need a little more person power. So if you're interested, just come on over and into that thread, maybe in the Friday channel, since it's kind of a community resource.
Yes, and maybe there's possibly also could be some more discussion on Friday about these kind of things. That would be great. Thanks. Benne.
I know Galaxy Zoo looks for merger remnants, right? So they have a button that says stream or remnant or something. Would that do? Is that the question that you're after? Or are you going more specifically like you see actual? I'm sorry for the beginner question here.
No, that's a good question. So back when we were talking about this before, what we actually hoped was that people would try to classify the morphology of the streams in order to give us an idea of the distribution of like orbital eccentricities that you get from looking at all these things, since the morphology is a function of eccentricity as well as mass. We were also hoping to see whether people could draw on the pictures to help us get a starting point for a stream track fitting. So we wanted to ask people to do more than just identify the streams, because that is already not terrible with machine learning, but more to like characterize them in a bit more dynamically relevant sense beyond just, is there a stream? Jeff, I don't know if you want to add anything, or Adrian.
Actually, would it be possible to build in some fitting method that people could play with, so that you already do like some minimal stream fitting, orbit fitting?
In fact, there is. When we had this discussion, Chris Lintott was showing us actually a really simple, it was crazy low resolution, but it worked remarkably well actually. Like you can do a super low resolution end body fit essentially to like the features that a user identifies in a tiny little PNG image. They can say, you can do like, 3 really low res end body fits and say which of these looks closest, and they can click that, and you could maybe even iterate on it. So there are things that you can do.
Because that would also raise participants. Because if you can connect them more to what the science really is, instead of only classifying, some people like that much more.
Yeah, and it also kind of gamifies it a little bit.
Exactly.
Yeah, I think we could go beyond that at this point, because GPUs are in most machines now, and you might be able to just have sliders that do it in situ, which is more doable now than before. We should revisit that, obviously.
Benne, is this a new hand or an old hand?
Old hand.
Okay, thank you. Sarah.
Yeah, this is kind of a topic change. Was that what you meant? Or should I just go ahead?
Then I'll first want to ask, is there anybody else who would like to comment on this?
Maybe Shani?
No, I'll go after Sarah. I also want to bring that.
Okay, Sarah, it's yours.
Yeah, this was actually based more on discussion earlier today, but I'm glad to see that we're also thinking more, and I think we should keep doing that, thinking more about dwarfs and streams and dwarfs, because in a lot of the local volume sample that we'll be able to do anything, follow up spectroscopically, et cetera, will be in dwarfs. And I think we saw from Jeff's work that we're only now starting to find these, and obviously Titske is working theoretically on dwarfs, streams and dwarfs, and then tracing back to the globular cluster streams that I'm excited about finding in external galaxies. A lot of these should actually also be in dwarfs. And I think Jorge left, but otherwise I was going to ask him. There's not a lot of theoretical work done on globular cluster disruption in dwarf galaxies, and you have different tidal fields, you might have different shapes, higher triaxiality. So I think that's something we should keep in mind, that dwarfs are really the galaxies that we have an abundance of nearby.
Okay, thanks. Anna.
Yes, I wanted to connect this to a topic that we just recently discussed at the end of our group, which is the question of how well do we know the sort of kinematics of a globular cluster population in a dwarf galaxy, as we are seeing now a number of streams sort of being tentatively associated with dwarf galaxies. And then I think that the question is kind of, do we have do you know how we would say populated distribution function? So I think our conclusion was that we still need to study these and simulations, but I think this would be a nice connection between observing these streams around dwarf galaxies outside of the Milky Way, and those this already wrapped inside of the Milky Way, and see if how these are different, and maybe touches on the question of different environments that was sort of brought up in the first session today.
Thank you. Shani, did you have something that connects to this?
Yeah, I just wanted to add one more thing that we sort of started to discuss in our group, which is what kind of follow-up data we're going to be able to obtain for external streams. And I feel like while the chat on Zoom, on Slack, sorry, was pretty hopeless, I think that I'm actually more hopeful after we talked now. So I think that we had some good ideas, and one of them was that we should really understand what's the sweet spot for this kind of follow-up to begin with. But then again, I think that we need sort of to lower our expectations. We're not going to get follow-up data that is as good as the Milky Way, but we can, for example, try. That's what we discussed. Look at different areas of the streams and see if there is any gradient in velocities. So, for example, using all of the new amazing IFUs available on all of the gigantic telescopes, all of the 10-meter telescopes. So we're not going to get radial velocities of individual stars, but we can get some information, and this is going to help a lot to constrain some of the models. So I mean, yeah. So we should start slowly and explore and see what we can actually obtain. But I'm not completely hopeless about it.
Okay, great. That's good to hear. Anybody, any other thoughts on that? Ding.
So I want to go back to the early point. I forgot what Sarah, I think, mentioned about whether we can see streams around the dwarfs. So what I thought could be wrong, and it would be good to if people can correct me, but I really feel like all the global cluster streams that we are seeing now shouldn't form around its own parent. Like, how can I say, the global cluster stream we are seeing nowadays in any galaxy, the host galaxy shouldn't be its own parent galaxy, because if they can form in those kind of, like if say a global cluster can form in around the Milky Way and then become a stream, then it should happen a while ago after its formation. So I feel like all of the global cluster stream should form in a much lower mass halo. That's why it can be puffy. And after its own parent subhalo get disrupted, then it itself get disrupted, and that's what we are seeing now. However, we can see the streams like the open cluster stream. So this Eridanus Pisces stream at solar neighborhood. So those are the streams that we can see nowadays, but it's because it was formed recently and it's young, and after it formed, it get disrupted. So those are the ones that are like, I feel the in situ formation. So I really doubt we can see any global cluster stream around a dwarf galaxy that where the global cluster was formed around that global that dwarf. Do people think it's different? Because that's kind of my feeling, but I mean, I don't really see anything from simulation. It's really just what my thought is.
I think Sarah has a comment on that.
Yeah, I don't have an answer. I just wanted to clarify that what I meant wasn't the local group volumes. I actually local group dwarfs. I meant the local volume dwarfs, so out to 7 megaparsecs. And I think just an important point to remember is that we've never seen a globular cluster stream in any other galaxy than the Milky Way. So I think it's too early to say could we or could we not see them in dwarfs. But I've linked to Jorge's paper from 2009. That's the only one I know of that's kind of exploring this. So just emphasizing again, I agree we need to study this more. So Ting's now asking, but is it an open cluster stream? No. Do you want to elaborate, Ting, or?
Yeah, so my point is, my understanding, my point is a halo stream. I completely agree that it is definitely not a halo stream. So my question is more kind of narrow in terms of like whether or not it's possible a halo stream can form around, and we can see nowadays can form around its own parent halos, dark matter halo.
Yeah, that's what I'm hoping that we can see, because so many of the nearby galaxies are dwarfs, but I don't think we really know yet, but anyone who knows should chime in.
And I want to also emphasize again, sorry, is when I say we cannot see doesn't mean observationally we cannot detect. I'm asking whether they exist. Because if I feel like if they get disrupted, they should happen a long time ago, as soon as they got formed. So it was when they were young. So like nowadays, after 10 gigayears, we should not be able to see them anymore. Sorry, talk so much.
Thank you. Anna.
I wanted to, anyway, yeah, I haven't done any work on this myself, but I think from Kathy's talk yesterday, like he was saying that like simulating global cluster disruption in dwarf galaxies, that you can, like if the galaxy scored, then you then wouldn't expect the globular clusters to start disrupting, but if it's cuspy, then you would. So I feel like the search that Sarah is proposing, you know, might be informative either way. If we see like streams or not could depend, like could tell us something about the density profile.
Thank you. Dennis.
I wanted to raise the same point that Anna just made. Yeah, just that I think there are simulations showing that, you know, we can disrupt globular clusters and dwarfs that do make streams like in the Milky Way, because that's what, you know, Kathy's work is about. But I guess one caveat to that is that, you know, that work hasn't been done with N-body 6 and other like super accurate collisional codes. So I think it is probably worth understanding how that picture looks with the kind of state-of-the-art collisional codes to see if the same picture arises with the kind of work that Marquiles was showing yesterday.
Thank you. Diederik.
Yeah, so just to briefly come back to the point that Ting raised about whether we see globular clusters getting disrupted now because the tidal field they're sitting in now is basically stronger than the one that they formed in. Or, you know, if many of them form disrupt initially, yes, there is a huge population of globulars, or at least it's a prediction that should have disrupted early on, because we also see in the Milky Way that the disruption rate of younger clusters, if you control for mass, disruption rate for younger clusters that are sat in the disk is much larger than for clusters that are orbiting in the halo. And the reason is tidal interactions with the cold interstellar medium. But after that, let's say you survive that initial very disruptive phase. After that, in principle, let's say you're orbiting in a dwarf galaxy, and you have a certain tidal radius there, then you're going to get stripped onto your new orbit within a bigger galaxy that dwarf is falling into, the moment that the tidal field in that new galaxy matches the tidal field that you're currently in. So the only modification that you might get is an eccentricity term on top of that. But to first order, the tidal field strength is actually a preserved quantity. The only way you can increase it is if the galaxy that you're sitting in is just accreting mass. Then it ends up slowly becoming stronger. But this is a factor of 2 effect. So by and large, the tidal field is actually quite similar.
I just want to ask for clarification, sorry. So what you are saying is it only happens when a globular cluster's parent subhalo fall into another host halo, and this disruption can happen. But if it's an isolated dwarf galaxy, then a globular cluster formed in the globular cluster formed in that parent subhalo, it won't get disrupted as time goes. Is that correct?
No, I think they would be disrupted at exactly the same rate because the tidal field strength is the same. So for the globular cluster, like as soon as it has migrated out of this gas-rich environment in which it formed, then further cosmological accretion and so on in its environment will not significantly change its disruption rate. So as soon as it's out of it, so if it's orbiting in the halo of a dwarf, it has a certain disruption rate, and that will be quite similar to the disruption rate it'll have after that dwarf accretes into a bigger galaxy. But I agree. So Adrian is commenting in the chat that eccentricity can vary. Indeed, I agree, and that can be a major point. But it would require an eccentricity that's relatively big. Otherwise, that won't do much. And the eccentricities are, just to clarify, in the lifetime of globular clusters, the eccentricity term is just factor 1 minus eccentricity in the total lifetime. So you would need to make it a factor 2 shorter lived, you would need an eccentricity of 0.5.
Dennis, I think this is still your hand up from before, I'm assuming, so I'm going to Raphael.
That's right. Yeah, sorry, I'm currently driving, so that's why I can't deal with that. Sorry.
Drive safely. Raphael.
Hey, I just wanted to comment on the tidal disruption of globular clusters inside dwarf galaxies. Namely, we've been working on similar questions with a student in Victoria who is studying the orbital decay of globular clusters in the joint tidal field of a dwarf and the Milky Way as a host. All I would like to say is that in Caspi dark matter halos, we know that globular clusters can decay there, and then the field strength for tides does increase over time. This decay timescale can be influenced from the Milky Way tides, which add onto the ones of the dwarf galaxy. So I wouldn't agree that the disruption timescales should stay the same just because the Milky Way tides add on top of the ones of the dwarf, and this changes how dynamic friction acts on the orbits of the globular inside the dwarf.
Isn't the difference there that Diederik was talking about when the globular cluster gets stripped off the dwarf, and you're talking about when it's still bound to the dwarf?
Exactly, yes. I'm talking of this pre-processing we've heard before in the last days inside the dwarf still.
Thank you. Anyone want to add to that? Does anybody who commented in the chat actually want to say something about that or not?
I can raise the point, or maybe hear what people are saying about the kind of the eccentricity depends on. So I think that's a really nice feature of going beyond the Milky Way, that then we can observe many systems and hopefully like have a large enough sample that we can get globular clusters around our galaxies on a range of eccentricities. So maybe just kind of to tie it back into the kind of more actionable items to bring up for discussion, what kind of, how many systems do we need, like that people would feel that we have kind of sampled the different orbital configurations of relevance.
Thank you.
Just to clarify though, I was talking about eccentricity that the cluster gets when it's stripped into the Milky Way, not the initial eccentricity within the dwarf, because you strip that roughly. You strip when, as Diederik was saying, when roughly your orbital period in the dwarf is the same as your orbital period would be in the galaxy that you're in now. Which is, you can also say the same thing about tidal radius or mean density or whatever. But that's just saying something about your mean orbit. Then you could, depending on what the orbit of the host galaxy was, you could be deposited on a very extreme or eccentric orbit, which then, shocking and other things become more important. So I think it's a really interesting open dynamical question, whether we expect to see them in the host galaxies.
So we should definitely work on that. Okay, Sarah first, then Diederik.
Yeah, I just wanted to go back to what Eugene said this morning, that this is showing that there's a lot to be done before we go to gap characteristics of globular cluster streams in external galaxies. I just kind of want to emphasize that I think this discussion has been really valuable in thinking of what are the important next steps that we can use these streams for in other galaxies, the thin ones.
Thank you, Diederik.
Yeah, so this is indeed is true. There are many globular clusters on quite eccentric orbits, and I really agree with Adrian. I think what is important though is that there were two options. Either the globular cluster in the progenitor dwarf was already in the halo of that dwarf, and that means it's already been kicked out once, and it means already probably was on an eccentric orbit. And then the question is basically, how much does your 1/e term change, right? That'll be the relative increase of the disruption rate as it is accreted into the new halo. And if E is already non-zero, then that just limits the possibilities there. If it was still sitting in the disk, well, then it was sitting in a hyper disruptive environment. And then when it gets accreted, then you would need to have its eccentricity be something like 0.99 in order to match the disruption rate it had in the disruptive disk. So by and large, it is actually, it's really hard to make the tidal disruption rate increase. But you're right. I mean, if it turns out the progenitor is just falling into a massive galaxy at a 0.9 eccentricity orbit, then that'll help a little bit. Yeah.
And except when the globular cluster then interacts with the Milky Way disk.
So yeah, disk shocking turns out is weaker than bulge shocking on a eccentric orbit typically. So yeah,
Okay.
this is a good point. But I think I forgot the paper. Maybe it's a Canadian moss tracker 97, but it's a bit weaker than the blood shocking.
Okay, thank you. So I think this is a great discussion and we're almost out of time. And I wanted to bring back the slides from the beginning actually with the questions. And I think we've combined the two topics in talking about the assembly of the Milky Way and its accretion and the globular clusters that fall in with it and connected it to the streams in external galaxies. So I think we did like a perfect job seeing the spread of topics of the day. So everyone, thank you very much for this awesome discussion.